Alright, so our first topic for today is lemmas on simple roots. Carrying on with this idea from last video of this simple root idea. Yeah, that's not great explaining, but you know what I mean. Okay, first off we have a lemma, as you would expect. If alpha is positive but not simple, then alpha minus beta is it's a positive root actually, for some beta in our basis. Proof. If the form of alpha and beta would be negative for all beta in our base, we would have, based on our last proof last time, that the base of some gamma is linearly independent. We'd have that the union of gamma, or delta, and our alpha is linearly independent, but we know that delta is already a basis of E, so alpha and beta, we have a beta such that the form of alpha with beta is positive for some beta in our base. So alpha minus beta is a root. So we can write alpha as the sum across gamma in our base of k gamma gamma with all k gamma strictly positive, and some are, well, strictly non-negative, some are strictly positive. This alpha minus beta yields a integer linear combination of simple roots with at least one positive coefficient. Thus all coefficients are positive. Positive by uniqueness. This comes with a corollary. Is that each beta in the set of positive roots can be written as the sum from I equals 1 to k of alpha I for alpha I in our basis, not necessarily distinct, such that each sum of I equals 1 to j of alpha I. Each partial sum is a root. And the proof is by our lemma. Don't know why I always capitalize the L in lemma. An induction on the height of B. Beta. Okay. Now there's another lemma we're gonna use. This one states that if alpha is simple, its reflection permutes the positive roots other than alpha. And the proof, I'm going to let beta be a positive root and not a alpha. And we can write it as the sum for gamma in our base of k gamma of gamma for positive k gamma. So beta is not proportional to alpha. And then k gamma is non-zero for some gamma distinct from alpha. With the coefficient of gamma in sigma alpha of beta, which we recall is beta minus the inner product of beta, the diagonal, the angle bracket of beta with alpha, scaling alpha, is still k gamma. So sigma alpha of beta has at least one positive coefficient with respect to our base, so it is positive. And since alpha is the image of negative alpha, we have that sigma alpha of beta cannot be alpha. And there's a corollary to this. We set delta to be 1/2 of the sum of our positive roots beta. Then sigma, the alpha reflection of delta is delta minus alpha for all alpha in delta. That's just by the lemma, just straightforward. So that brings us to another lemma. we have a collection of elements in our base, not necessarily distinct. With a reflection for each element. If the composition of all these up to the last one of alpha t is negative, then for some index s, calling it an index to make it clear that it has to be between 1 and t, the composition of sigma 1 all the way through sigma t is sigma 1, the composition of sigma 1 up until sigma t, but skipping over sigma s. Let beta I be the composition of sigma from I plus 1 up until sigma of t minus 1 of alpha t. T with beta of t minus 1 then equal to alpha t. Since beta 0 then is negative from above, and beta t minus 1 is positive, we can find a smallest s such that beta s is positive. Then sigma s of beta s is equal to beta s minus 1 is going to be negative. So by the previous lemma, we have that beta s is equal to alpha s. In general, if sigma is from the weyl group, then sigma of sigma of alpha is equal to sigma alpha sigma inverse. Which means that sigma s is sigma s plus 1 through, not plus 11, plus 1 composed through to sigma t minus 1, sigma t of sigma s plus 1 through sigma t minus 1, which gives us our lemma. And this comes with a corollary that f sigma can be written as the composition of sigma 1 through sigma t is an expression for sigma in the weyl group of reflections corresponding to simple roots with minimal t, then sigma of alpha t is negative. So again, it's immediate, and we can go ahead and move on to our next chapter, which is going to be on the weyl group. Now, in this chapter, we're aiming to prove that the file group permutes the bases of our root system, which is the same thing as permuting the file chambers in a simply transitive fashion, and that the file group is generated by the reflections relative to any base. Alright, and so we start out with the theorem. And yeah, we have a root system phi with a base delta. If gamma is a vector in E, which is regular, there exists a symmetry sigma in the file group such that sigma of gamma on alpha, the form with alpha, is positive for all alpha in our base, which means that the file group acts transitively on file chambers. Delta prime is another base of phi. Then sigma of phi prime is phi for some sigma in the file group. For all roots alpha, there exists a symmetry in the file group such that sigma of alpha is in our base. D, we say that the file group is generated by the sigma alpha for alpha in the base. E, if the sigma of a base is the base, and sigma is for some sigma in the file group, obviously, then sigma is just the identity. So the file group acts simply transitively on bases. For a proof, we're going to let W prime be the subgroup of the file group generated by all of the reflections generated by the elements of the base. So we're going to do let's prove the first three steps just for this subgroup, and then show that it's the whole thing, which means our previous results will then apply to all of the file group, and not just the subgroup. Once again, we're going to let delta be 1/2 of the sum of the positive alpha. Keep in mind we're proving that if we have a regular vector, then there's a sigma such that the form of sigma of our vector on anything in the base is positive. So we're letting delta, and we're going to choose an element of the, I'll call it the lesser file group, I don't know if that's the thing, for which the form of sigma on gamma and delta is maximal. If alpha is simple, then sigma of alpha on sigma is in the weyl group, the lesser weyl group, that is. So the choice of sigma implies that we got a string of equations here, I think too long for writing on one line, so gamma of delta, the form of gamma of sigma of gamma with delta is at least the form of sigma alpha sigma of gamma with delta, which is equal to just sigma of gamma sigma alpha of delta which is just sigma of gamma delta minus alpha by our previous lemma, which is then just sigma of gamma on delta minus sigma of gamma on alpha. We can split that across our form. Thus, the form of sigma of gamma and on alpha is positive for all alpha in our base. Since gamma is regular, we cannot have any sigma of gamma with any alpha being 0. Because our gamma would be orthogonal to sigma inverse of delta. Sigma inverse of alpha, sorry. So all inequalities are strict. Thus, sigma of gamma lies within the weyl chamber of our base and sends gamma sends the weyl chamber of gamma to the weyl chamber of our base. Now, part B, which states that if we have a second base, delta prime, there's an element of the weyl group sending delta prime to delta. Which is, we can see that's just from A in the obvious manner. Because keep in mind, we have this connection between weyl chambers and bases. So we can just use that. C states that for any root alpha, there's a sigma in the file group sending alpha into the base. And from B, we only need to show that every root belongs to a base. Since the only roots plus or minus alpha are proportional to alpha, the hyperplanes of p beta are distinct from p alpha for beta not equal to positive negative alpha. So there exists gamma in p alpha and not in p beta. I guess we'll write it like this. And gamma is not in p beta for all beta not equal to alpha, not equal to positive minus alpha, obviously. Choose gamma prime, close enough to gamma such that the form of gamma prime with alpha is a positive epsilon, while the absolute value of gamma prime and beta is greater than epsilon for all beta not equal to positive minus alpha. Thus, alpha belongs to the base generated by gamma prime. Next we have statement D, which is that our lesser weyl group, whatever I called it, is just the weyl group. And we will just show each reflection alpha for all alpha in root is in W prime. From C, find a gamma in the lesser weyl group such that beta is just sigma alpha in our base. Then sigma beta, the reflection of beta, is the reflection of sigma alpha, is the conjugate of sigma alpha by sigma. So sigma alpha is just the conjugate of sigma beta by the conjugate of sigma, I guess sigma inverse of sigma beta, which is in the lesser weyl group, which is just the weyl group. And finally, we want to show that if an element of the weyl group preserves a base, then it is the identity. So we're going to let sigma of our base be the base, and assume that sigma is not just 1. Then we can write sigma minimally as a product of reflections, contradicting our third I think lemma, and we're done. Now we're going to use our lemmas to explore what it means that the while group is generated by simple reflections. So when sigma in the while group is written as the product of sigma alpha 1 through to sigma alpha t for alpha I in our base and t minimal, we call the expression reduced. And we write that the length of sigma is just a number of elements in this expression. This is the length of sigma relative to our base in question. With our unit symmetry just being reduced to the empty set, and the empty product. We have an alternate way to think about length, which we can define n sigma to be the number of positive roots alpha with sigma of alpha being negative. And now this comes with a lemma which just states that the length of a element of the while group is just the same thing as this new function, and our proof. By induction on our length, and we see that the base case is where the length is 0, the identity case, and obviously that's not going to turn any roots negative, any positive roots negative, so n is going to also be 0, so it matches up there. Let the lemma hold for length less than our sigma. We write sigma in reduced form as sigma is equal to sigma alpha 1 multiplied through to sigma alpha t, and set alpha to be our last alpha in this chain by our third corollary sigma of alpha is negative, so by the second lemma n of sigma times sigma of alpha is n of sigma minus 1. And we also see, we see that the length of sigma alpha, in reduced form, that's just going to cancel out the last term. So that's just going to be the length of sigma minus 1. So by the induction hypothesis, we can match these up and we are done. Now we're going to look at the simply transitive action of the Weyl group on Weyl chambers. You'll see that the closure of the fundamental Weyl chamber of the base delta is a fundamental domain for the action. This I'll write down. Next we show that the closure of the Weyl group of the Weyl chamber of delta is a fundamental domain for the action of the Weyl group on our Euclidean space that is each vector in E is conjugate by the Weyl group to a unique element in the closure of our delta chamber, Weyl chamber. And, alright, let's look at the lemma. Let lambda and mu be in the closure of the delta Weyl chamber. If sigma of lambda is equal to mu for some sigma in the Weyl chamber, sigma is a product of simple reflections which fix lambda so that lambda equals mu, obviously. The proof, once again, induction on the length of sigma, with the base case being trivial. Let L sigma be positive. So by our first lemma, sigma sends some positive root to a negative root. So sigma cannot send all simple roots to positive roots. Say that sigma alpha is negative for some element of our base alpha. Now we have that mu of the form of mu and sigma alpha has to be negative. It also has to be equal to the form of the inverse of sigma on mu with alpha, which is equal to lambda alpha, lambda, the form of lambda on alpha by assumption, which is positive as lambda and mu are in the closure of the Weyl chamber of the base. Thus, the form of lambda and alpha is 0, and sigma alpha preserves lambda. So sigma times sigma alpha of lambda is mu. By two of the previous lemmas, the first two, we have that the length of sigma alpha is the length of sigma minus 1. So by the induction hypothesis, we are done. And that's the end of this lemma and this chapter, I think. Yeah, and we're like, that's just about a video length. And once again, we're like one section away from ending the chapter. I'm like they made each chapter, each full chapter, like a video length, or like 2 video lengths, and I'm just been off by 1 this whole time. It's kind of annoying. But anyways, I mean, I don't know. We will be taking a break from this book at some point, but I don't know when. Probably not anytime soon, I don't think.